Hi everyone, and welcome to the second part of the Chapter 4 lecture. So Chapter 4 is all about chemical bonding. And in the first half, we defined ionic bonding and covalent bonding, and we learned how to identify ionic and covalent compounds and how to name them, and how to write ionic compound formulas. So those are processes that follow a set of rules that you just have to practice in order to get them down straight. The second half of the chapter, we're talking more about why those types of bonds form and how the atoms actually combine in order to form these bonds. And so there are various different bonding theories to help explain why atoms bond and how they bond. So the four different theories are the Lewis model, the Vesper model, it's spelled V-S-E-P-R, but it's pronounced Vesper by chemists. The valence bond theory, and I'll just abbreviate that as VB, and then also the molecular orbital theory, or MO for short. Now, each of these is sort of, the Lewis model is the simplest, and the molecular orbital theory is the sort of most complex, kind of similar to how we had the Bohr model of the atom as being the simple model, and then, quantum mechanics being the more advanced model. So we will go through the Lewis model and the Vesper model. I'll touch a little bit on the valence bond theory, just a tiny bit, but I'm not going to talk about molecular orbital theory at all. So both of these are sort of advanced. They're in Chapter 5, and we're skipping most of Chapter 5. I'm just going to touch on a little bit of the valence bond theory. But again, I think that we're just going to cover the Lewis and Vesper models. All right, so speaking of the Lewis model, the Lewis model. All right, so the Lewis model uses these electron dot structures. So the electron dot structure is where we write the element symbol with dots around it to represent valence electrons, just the valence electrons, which remember are the outermost electrons. And so we can think of each element symbol, that this is an element symbol, excuse me, that it has sort of four regions, north, east, south, and west. All right, and we can put, two electrons in each spot, but we put them in there one at a time before we form pairs. So a valence shell is full with 8 electrons, so we could put a maximum of 8 electrons in here. Okay, so I'm just going to show you the dot structures for the first, I don't know how many this is, first 10 elements on the periodic table. So we've got hydrogen. Hydrogen is a group 1A element, so it has 1 valence electron, so we're just going to draw 1 valence electron there. You could draw it on the top or on another side. I don't think there's a real, I don't know what word I'm looking for, like a standard where you start drawing them. Helium has 2 valence electrons, all right? And both of those electrons are actually going to be paired together. That's because in the first row, the first orbital, the first energy level has 1 orbital, and you can fit 2 electrons in there. So those first two elements are full with 2 valence electrons. All right, that's the max they can hold. All right, everything else basically down the periodic table can hold 8 valence electrons, more or less. All right, so now we're in the second group, or the second row of the periodic table. Still in group 1A with lithium, so lithium has 1 valence electron, so its dot structure would look like this, lithium with 1 valence electron. Beryllium is in group 2A, so its dot structure would look like this, 1, 2. Okay, we don't pair its electrons. We're going to write in a circle around. So then 3A, we've got boron. So we're going to do 1, 2, 3. Sorry, my dots are a little messy. All right, carbon is 4A, so its dot structure looks like this. Nitrogen is group 5A, so we're going to do 1, 2, 3, 4, 5. So we've got a pair on top and then 3 singles. Group 6A elements, 1, 2, 3, 4, 5, 6. I know I like symmetry. 7A is going to have 1, 2, 3, 4, 5, 6, 7. And then neon and all the other noble gases will be full with 8. So we'll go ahead and just draw all 8 valence electrons. All right, so remember that group number is our way that we can use the periodic table to sort of cheat and figure out valence electrons without actually having to write out the electron configurations. We can just use the group number to predict valence electrons. So just remember, all elements in a group have the same number of valence electrons, and it's the number of the group. Alrighty, so of course we know that elements are most stable when they have a full valence shell. The noble gases are incredibly stable, and basically all other atoms on the periodic table of all other elements really want to be like the noble gases and have a full valence shell. So they follow what's called the Octet Rule, which we mentioned already, but it's always good to reinforce, all right? That elements are most stable when they have a full valence shell, and that for pretty much all elements, that is when they have 8 valence electrons, when they have that electron configuration that ends in N2p6. All right, transition elements are sort of an exception. The duet rule applies to hydrogen and helium because they're both full with 2 electrons because they only have a 1s2 orbital. All right, so these valence electrons and the octet rule, they basically govern bonding. And bonding happens when elements either gain or lose or share electrons in order to fill their valence shell. And we saw that when we defined covalent and ionic bonding. So ionic bonding involves gain and loss of electrons, and covalent bonding involves sharing of electrons. Now, I like to put this disclaimer in here, like any good rule, there's always exceptions. And a theme that you'll see in this class is that I will often tell you about some of the exceptions as like an aside, but I don't test you on exceptions because I feel like at the introduction level of chemistry, you should learn and master the rules, and that exceptions oftentimes just become distractors and confusing distractors that get in the way of you learning the rules. So I'd rather you learn the rules first, and then in later courses you can learn to master those exceptions. All right, so let's talk ionic bonding for a second. Ionic bonding is the transfer of electrons, so gain and loss, in order to form ions with opposite charges that attract. So for example, if we use the Lewis dot structure here to illustrate this, if we have lithium, which has 1 valence electron, and chlorine, which has 7 valence electrons, and I'm drawing the dot structures here. All right, so basically what happens is lithium loses an electron to chlorine. And so we end up with a lithium ion that's positively charged because it's lost an electron, and a chlorine ion that's negatively charged because it gained an electron. And those two attract each other to form an ionic bond and an ionic compound with the formula LiCl, lithium chloride. All right, here's another example. Sodium, group 1, has 1 valence electron. Oxygen, group 6, has 6 valence electrons. All right, so sodium, we're going to need 2 of them in order to fulfill oxygen's octet. So 1 sodium will lose an electron, this sodium will lose an electron, and we end up with sodium plus ions, 2 of them, and an oxygen 2- ion to form the ionic compound sodium oxide, Na2O. All right, so the dot structures kind of help us to visualize that transfer of electrons that happens in ionic bonds. All right, it also helps us to visualize what's going on in covalent bonding. So now for some talk about covalent bonding. All right, this is of course sharing of electrons between 2 atoms. So how do atoms share electrons? Well, let's do this with water. So let's use water as an example. So water is hydrogen, oxygen, and hydrogen. So if I have these 2, or these 3 atoms here, right, and I'm just going to draw a circle to sort of represent the cloud, the electron cloud, the space that those electrons are actually flying around in. All right, so I have 3 atoms, individual atoms here. So what happens in a covalent bond is those atoms get close together and overlap their orbitals. All right, so we end up with a picture that looks like this. All right, there's fix my hydrogen. All right, and if I just, maybe if I color code a little bit here, the hydrogens are red, so one of those electrons came from the hydrogen. So you can see that they're sharing electrons by basically getting close together and overlapping their clouds. So these electrons here, the ones that just belong to the oxygen and are only found in the cloud around oxygen, these are called lone pairs. All right, and I'm going to put that down here, fill in this blank. All right, lone pairs are also called non-bonding pairs, and they are pairs of electrons that are not shared, so they belong to one atom and that atom only. These electrons here in this shared region, all right, where there's the overlap, those are bonding pairs of electrons. And we'll fill that in down here, bonding pairs. So those are pairs that are shared. And we could write this molecule out, we could write this out in a Lewis structure where we show the bonding pairs as a line and the lone pairs still as their 2 dots. All right, so these are also, this represents a bonding pair. A line, all right, a bond line, one bond line actually represents 2 electrons. So you can think of it as like there's actually 2 electrons here that are being shared in that bond. All right, so when elements are sharing an electron, I say they think, quote unquote, that it owns those shared electrons. So therefore they each fulfill the octet rule. If we're looking at hydrogen over here, okay, hydrogen has 2 electrons, one that it belongs to it and one that it's sharing with that comes from the oxygen. So, but because they're sharing, now hydrogen has 2. So it fulfills the duet rule. And oxygen, because it's sharing electrons with hydrogen, has 1, 2, 3, 4, 5, 6, 7, 8, and it fulfills the octet rule. Okay, so bonding, covalent bonding also allows atoms to fulfill the octet rule through sharing rather than transfer of electrons. So in this water molecule, we have 2 single bonds. All right, you can have single bonds, double bonds, and triple bonds. And we call that the bond order. So multiple bonds contain multiple electrons, multiple pairs of electrons. So a single bond is, of course, made of 1 shared pair, which is 2 electrons, and we call that a bond order of 1. A double bond has a bond order of 2. and it is 2 shared pairs, which means 4 shared electrons. And a triple bond has a bond order of 3. It has 3 shared pairs for a total of 6 shared electrons. So some examples of each of these. So with H2, hydrogen gas, all right, the Lewis structure looks like this. All right, it's a single bond. In other words, you have a hydrogen with one and a hydrogen with another, and they are sharing those 2 electrons there. Oxygen gas, O2, would be an example of a double bond. All right, the Lewis structure of O2 looks like this. Some lone pairs and some shared pairs. So essentially you've got oxygen has 6 valence electrons. I'm going to do it kind of like this. Oh wait, no, I did that wrong. So you've got oxygen, and it has 2 shared pairs here. So each oxygen has 6 valence electrons, but by sharing those 2 pairs, lining up those 2 pairs and overlapping their orbitals, like so, they're sharing 2 pairs of electrons. Okay, and then nitrogen gas, N2, is a great example of a triple bond. This is what the Lewis structure looks like. All right, so we've got nitrogen has 5 valence electrons. It's going to share 3 pairs though. All right, so you can think of them overlapping their orbitals like so. And something like that, okay? So there's some general patterns that you're going to see when we're working with Lewis structures, because again, the number of bonds that form is related to the number of valence electrons that atoms have. You're going to see certain patterns. So so hydrogen and the halogens, which is group 7A. All right, hydrogen has 1 valence electron. It needs 1 more, so it tends to form 1 bond. And the halogens, like fluorine, have 7 valence electrons. All right, so they need 1 more, so they tend to form 1 bond. Oxygen and other group 6A elements have 6 valence electrons. It's a little bit sloppy. I'm going to fix that. All right, 1, 2, 3, and 4. All right, so they can have 2 bonds. I like to think of the bonds as sort of filling or growing from those single electrons. So oxygen can have 2 single bonds. Actually, I'm going to draw this more linearly. All right, oxygen can have 2 single bonds, or oxygen can have a double bond coming out of it, and then 2 lone pairs. In group 5A, like nitrogen, all right, nitrogen has 5 valence electrons, so it can have 3, has room for 3 more valence electrons, so it can have 3 bonds, and it can do this in a couple of ways. It can have a double and a single bond, or it can have a triple bond. All right, so as we're going down, we're kind of getting more and more flexible. And then lastly, group 4A namely carbon, can have 4 bonds. So carbon can have 4 bonds coming out like this, or it can have 2 single bonds and a double bond, or it can have, can have 2 double bonds, or it can have a single bond and a triple bond. So carbon has is sort of the most flexible. It can take on the most different types of shapes, and that's why there's a whole field of organic chemistry that studies carbon-containing molecules, because there's so many different molecules that can contain carbon at the center. They can form these long chains, and then you can have branches off of them. So it's a whole area of chemistry, and the whole reason it exists is because carbon can have so many different bonds, more than others on the periodic table. Alrighty, so we're really talking about covalent bonding heavily in this chapter because we don't draw ionic bonds out like this. We're talking about when we draw Lewis structures, and we're talking about bonding patterns and molecule shapes. We're talking about, the key word there is molecules, which are covalent compounds. So remember, covalent compounds involve sharing of electrons, but not all sharing occurs equally. And that is due to something called electronegativity. Electronegativity. So electronegativity is sort of the strength of pull that atoms have on electrons in a covalent bond. So when atoms are covalently bonded, there's sort of a tug of war, if you think about it that way. I like to think about it that way, on those electrons, depending on which atom is sort of stronger, has a stronger pull. So this table here shows you different electronegativity values for the different elements, and you can see some trends. It's sort of 3D and raised. You can see that electronegativity definitely increases as we go right across the periodic table, with the exception of hydrogen. So the non-metals have a higher electronegativity than the metals, right? With another exception being those noble gases have 0 electronegativity because they don't bond. They don't react with anything, so they don't have any pull on electrons in a bond because they don't ever bond. So the electronegativity sort of maxes out right here. And the biggest electron hogs on the periodic table are fluorine, oxygen, nitrogen, and chlorine here. I call them the electron hogs, and my mnemonic to remember them is phone call. F-O-N-C-L, phone call. I don't know, maybe some kind of mnemonic about making a phone call to the electron hogs. Water break. Okay, so whichever element in a bond has the highest electronegativity, that's what En means, that one will have a stronger pull on electrons. So maybe let me show you what I mean. Okay, so we've got, let's take this example, hydrochloric acid, HCl. All right, the electron negativity of hydrogen, if we look at the periodic table, at this electronegativity table, is 2.1, and the chlorine is 3.0. Okay, so the chlorine is stronger. It has a stronger, higher electronegativity, a stronger pull on electrons. All right, so that means thus the shared electrons will actually be closer to the chlorine in this bond. All right, I think of it kind of like shared custody in a divorce. It's called shared custody, but you don't always spend equal time with each parent. My parents are divorced, and I spent every other weekend with my dad. So my mom was sort of more electronegative in a sense that she spent more time with the kids. So chlorine in this situation has a little more custody in this shared custody agreement. All right, since electrons are negative, this is going to result in charge dispersion. So this results in what we call partial charges. And we represent them with the Greek letter delta. So that means a partial positive charge and a partial negative charge. The question is, which one is partial positive and which one's partial negative? So chlorine is the one that's pulling on electrons. The electrons are negatively charged, so that's going to give the chlorine a partially negative charge. And it's taking those electrons away from the hydrogen. It's going to leave it partially positively charged. And this arrow, which was supposed to be deleted so I could draw it myself, all right, is called a dipole moment. And we draw it like this. It's like a vector arrow. And it just shows us the direction that electrons are actually being hogged towards. So they'll always point, that dipole moment is what it's called. That arrow is called a dipole moment. And it just shows the direction the electrons are being pulled. Okay, so these electronegativity differences create unequal sharing conditions, all right, and what leads to bond polarity. So bonds can be either polar or nonpolar. So we'll start with a nonpolar bond. Now, polar and nonpolar are both describing covalent bonds. So a nonpolar bond is by definition a covalent bond. So the more complete, you could say a nonpolar covalent bond, but usually people don't say the covalent part. They just know it. All right. So in this case, nonpolar bonds occur when there is equal sharing of electrons. All right. So when the difference in electronegativity value is small, somewhere between 0 and 0.4. All right, so this is the case whenever you have two identical atoms bonded together. So chlorine and chlorine, hydrogen and hydrogen, nitrogen and nitrogen, oxygen and oxygen. I mean, keep going. If it's two of the same atom, then they're going to have equal electronegativities. An example where there's two different atoms bonded together that have similar electronegativities is carbon and hydrogen. Hydrogen has an electronegativity of 2.1 and carbon is 2.5. So the difference in the electronegativity, that's what that little triangle means, is 0.4, which is pretty small. So we consider this bond here to be a nonpolar bond. A polar covalent bond is one where there is unequal sharing of electrons, where there's a sort of intermediate difference between the different electronegativities. So the example we did before with chlorine, all right, the electronegativity of each of these was 2.1 and 3.0, so that's a difference of 0.9, all right. Carbon and fluorine. Carbon has an electronegativity of 2.5, and fluorine's electronegativity is 4.0. So the difference between them is 1.5. All right, so any difference that's somewhere between roughly 0.5 and 1.8, all right, it's not exact always, but roughly, is going to result in a polar bond, okay? And I like this little cartoon over here showing chlorine in this tug of war and the sharing of the two electrons. Those electrons are closer to the chlorine. The chlorine has a stronger pull. It's more electronegative. It's hogging those electrons, all right? And then technically on this scale still is ionic bonding. And ionic bonding involves transfer of electrons to form ions, and that transfer occurs because of electronegativity differences. If the electronegativity difference is very great, that the stronger atom is so strong it actually pulls electrons away from the weaker one. So metals are very weak. If we go back here and look at this scale here, the electronegativity values of the metals is very low. And so when they are bonding with nonmetals, all right, the difference is going to be very great, which is why metal plus a nonmetal equals an ionic compound. It's because the electronegativity of the nonmetal is so great, it rips electrons away from the metals. So I could calculate them for all of these guys, but I won't. You could do that yourself and see. So the neat thing to me is that, in like maybe high school, elementary school, you learn the different types of bonding, ionic and covalent. There's 2 different types of bonding. But really, in actuality, it's really all the same. Bonding occurs along this continuum. It's all a matter of electronegativity differences. So if 2 atoms have the same electronegativity, they will share electrons equally. If they have slightly different electronegativities or intermediately different electronegativities, they will share unevenly and end up with partial charges. But if they have really great differences in their electronegativities, then the stronger one will actually pull electrons away from the weaker ones, and you get full ions with full charges that are then held together by their opposite charges. And so another way to say this is that as we increase the difference in electronegativity, we increase the ionic character of the bond. So sometimes you might see questions that, are asking about polar compounds and saying that, like polar compounds have more ionic character than non-polar compounds. But of course, ionic compounds will have the most ionic character. But the polar covalent compounds have ionic character in the sense that they do have partial charges. So they're not fully ions, but they do have these pseudo charges. All right, so just a quick test your knowledge. Is the bond between each pair of atoms nonpolar, polar, or ionic? So you can use the periodic table, or you can use the electronegativity table to figure this out. So SR and F, strontium is a metal, fluorine is a nonmetal. I don't even need, if I know that, or if I looked at the periodic table and saw that, I really don't even need to know their electronegativities to know that this is going to be ionic. But to prove it, I will scroll up here. So strontium is 1 and fluorine is 4 in terms of electronegativity values. All right, so this one has an electronegativity value of 1, and this one has an electronegativity value of 4. So the difference in electronegativity is 3, which is definitely greater than 1.8. It's definitely going to be ionic. Nitrogen and oxygen. All right, this is a nonmetal and a nonmetal, so this is going to be covalent. If I go back to that table, I'm going to find that oxygen, nope, I got to look it up. Thought maybe I knew it. Nitrogen is 3.0 and oxygen is 3.5. Nitrogen has an electronegativity of 3.0 and oxygen has an electronegativity of 3.5. So the difference in the electronegativity values is 0.5. That's kind of on the cusp, but definitely in the realm of polar. That would form a polar bond because it's greater than 0.4. And then nitrogen and hydrogen. Nitrogen is, we just said, has an electronegativity of 3.0, and hydrogen we saw earlier had an electronegativity of 2.1. The difference here is 0.9, which is definitely going to be in the realm of a polar bond. All right, so we're going to come back to that in a bit, so don't forget the rules about polarity. All right, but now we're going to talk about how to draw Lewis structures. So we were just drawing really simple Lewis bonds and some very simple Lewis structures with like H2, O2, and N2. All right, so now we're going to draw some slightly more complicated ones. So these are the rules for drawing Lewis structures. I'm going to list them and then we're going to work through some examples. So the first thing is you want to add up the total number of valence electrons of all the atoms in the molecule. Let's just go ahead and start with an example. So let's start with CCl4, carbon tetrachloride. All right, so the first thing we're going to do is add up the total number of valence electrons here. So carbon has 4 valence electrons, And chlorine has 7 valence electrons, and there's 4 of them. So 7 times 4 is 28, plus 4 is 32 electrons. All right, so we added up the total number of valence electrons in all the atoms of this molecule. Next, we're going to lay out the atoms and connect them with single bonds. We have carbon and 4 chlorines. We want to have the least electronegative atom in the center. So chlorine is one of the hogs, one of the 4 hogs. If we look at that electronegativity table, we find that carbon has a lower electronegativity. So we'll put carbon in the center, and we'll put those 4 chlorines around it like so. All right. If we had any hydrogens, hydrogens always go around the periphery. They never can go in the center because they can only have 1 bond. They can't be in the center of anything. All right, so we laid those out. Now we need to distribute the rest of the electrons around the outer atoms. All right, so these 4 lines represent 2, 4, 6, 8 electrons of those 32 that we've already distributed. So now we need to distribute the rest. So we've got 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. All right, so now I have distributed all of the electrons. Now I want to see, does the center atom have an octet? Does everyone have an octet? Carbon has 2, 4, 6, 8. Yeah, and each of these chlorines also has 8. Because remember, we count those bonding pairs for each atom. So everyone has an octet. I double checked that. This is complete. Let's do another one. Let's do CO2, carbon dioxide. Carbon dioxide, start with our total number of electrons. So we've got 4 electrons in valence electrons in carbon, and oxygen, there's 2 oxygens, and oxygen has 6 valence electrons, group 6. So that's 12 plus 4 is 16 electrons. So there's 16 electrons we're going to need to distribute. So we're going to start, now we're going to go to step 2. We're going to lay out the atoms with carbon in the middle. All right, and the oxygen's on the outside. Cool, so we've used 4 electrons in those bonds. And now we need to go to step 3, distribute the rest of the electrons around the outer atoms first. All right, so we've got 2, 4, 6, 8, 10, 12, 14, 16. Okay, so now I have all 16 electrons accounted for. Now I need to see if the center atom has an octet. Carbon here does not have an octet. It only has these 2 bonding pairs, so that's 4 electrons. So what we're going to do is we're going to move some of these electrons. We're going to take a pair of these and a pair of these and move them to share them. So oxygen is going to share more than 1 pair. So the way that we would draw this is carbon now has a double bond with this oxygen, who has only 2 lone pairs left, and a double bond with this oxygen, who has 2 lone pairs left. Now we'll double check our octets. Oxygen has 2, 4, 6, 8, and carbon has, I want like a cursor. I don't know how to do that though. Oh well. So the oxygen has, let me see if I can do it this way. The oxygen has 2, 4, 6, 8. The carbon has 2, 4, 6, 8. And this oxygen has 2, 4, 6, 8. Okay, so everyone has an octet. So that is the correct Lewis structure, and I'll just redraw it cleanly. C, O. And don't forget your lone pairs. It's important to visualize those. All right, I have 2 other examples for us to work through. And the next one is CH2O. All right, so if we do the first step, we need to count the total valence electrons. Carbon has 4. Hydrogen, there's 2 of them, and each hydrogen has 1. And oxygen has 6 valence electrons. So the total number of valence electrons that are involved in bonding here is 4 plus 2 plus 6, which is 12 electrons. All right, so we're going to start with the least electronegative atom in the center, and that's got to be carbon. It can't be hydrogen because hydrogen has to be out on the ends of things. So we can do an H and another H and an O. We've just distributed all these atoms around the carbon. And I've used 6 electrons in the process, but there's 12 total electrons. So I'm going to add those last 6 here to the oxygen. We're going to distribute, that's step 3, distribute the rest of the electrons around the outer atoms first. Now we check, does the center atom have an octet? Does carbon have an octet? No, it does not. It only has 2, 4, 6 electrons around it. So what do we need to do? We need to share some more electrons. We're going to make a double bond here. And so we end up with carbon bonded to 2 hydrogens and double bonded to that oxygen, which now has 2 lone pairs left. Now everyone fulfills the octet rule, except for the hydrogens that fulfill the duet rule, and we've got our Lewis structure. So the last one is nitrogen gas, N2, and there's 2 nitrogens, each have 7 valence electrons for a total of 14 electrons that we need to distribute. So we're going to take those 2 nitrogens and connect them with a single bond and distribute the rest of the electrons. So we've got 2 electrons, 4, 6, 8, 10, 12, 14. All right. So both of these, what did I do wrong here? 2, 4, 6, 8, 10, 12, 14. Oh, I did this wrong. Okay. Nitrogen does not have 7 valence electrons, guys. It has 7 total electrons. It has 5 valence electrons. Did you catch that? Who caught my mistake before I did? Anyone? No? Okay, so let's fix this. So 10 electrons total, so 2, 4, 6, 8, 10. So there's 10 right there, okay? So as written, this does not meet the octet rule. Neither of these nitrogens have 8 valence electrons. So we're going to need to do some more sharing, all right? So if we share 1 more pair of electrons, then we'll have, see this situation, a double bond. All right, so now the nitrogen on the right fulfills the octet rule. It has 8 valence electrons, but the one on the left only has 6. So that's not going to cut it. We're going to need to share some more electrons. So I'm going to push another pair of electrons into this bond here. And so now we get N3 bonds, and each one has a lone pair. Now each of them has a complete octet. Now each of them is has 8 electrons that it has through lone pairs and shared pairs, and there's still only 10 electrons that we've distributed, okay? So this is how you draw Lewis structures. So I'm going to do one more here, maybe pause the video and see if you can draw this one, C2H4. All right, make sure you follow the steps, and I will do it outright here. So let's see, we've got 2 carbons with 4 valence electrons each, and 4 hydrogens with 1 valence electron each. 8 plus 4 is 12 electrons. So I'm going to put my carbons together because they have to be at the center. And then the hydrogens, there's 4 of them, and I'm just going to distribute them symmetrically. So give each carbon 2 hydrogens. So now I have 2, 4, 6, 8, 10 electrons. I need 2 more electrons to have 12. So I can't put them on the hydrogens because they're full already with 2. So I put them on this carbon here. But now this looks funky. So the carbon on the left has too many electrons and the carbon on the right doesn't have enough electrons. But if I share these, if I push those to be a shared bond, all right, now I still have 12 electrons, 2, 4, 6, 8, 10, 12 in my 6 bond lines there. And each carbon now fulfills the octet rule. They each have 2, 4, 6, 8 around them that they're getting through sharing of electrons through those bonds. Okay, so that's some Lewis structure practice for you. Again, you're going to need more practice with that. We are going to draw some more Lewis structures right now, though, for ions, for polyatomic ions. So you met these guys earlier in the chapter when we were doing ionic compounds. So polyatomic ions, really what they are is they're covalent molecules that have gained or lost electrons, and so then they carry a charge. So they're ions because they're charged, but their core is actually covalently bonded. So we can draw the Lewis structure for anything that is covalently bonded. And because they are charged, we have to either add or remove electrons in order to account for those charges. So for anions that are negatively charged, we have to add electrons to equal the charge. And for cations, which are positively charged, we have to subtract electrons. So let's show that for hydroxide, OH-. So oxygen has 6 valence electrons, and hydrogen has 1 valence electron, and that negative charge is from an additional electron that has been added. So hydroxide ion has 8 electrons total. So we can draw the O and the H connected. There's 2 electrons here in the bond, and we'll distribute the other 6 around the oxygen. Ta-da! So to identify that this is a polyatomic ion, we put brackets around it and we indicate the charge. So that's sort of the last rule for drawing Lewis structures of polyatomic ions. Let's do a couple more. Ammonium, Nh3+. Nitrogen has 5 valence electrons, plus the 4 times 1 valence electrons in the hydrogen, all right? But that plus charge means we lost an electron. So it's going to be 5 plus 4 minus 1, which is also 8 electrons. So we're going to do the nitrogen. We're going to put all those hydrogens around it, all right? Nitrogen has 8 valence electrons. It fulfills the octet rule. Each of those hydrogens has 2 through bonding, fulfills the octet rule, and we've distributed all 8 electrons. So we just draw our brackets and our positive charge. Boom. Lastly, we've got carbonate, CO3 2-. Carbon has 4 valence electrons. Just using the periodic table to see what group number it's in. I have 3 oxygens. Oxygen is in group 6A, so that means it has 6 valence electrons. And there's a -2 charge, so that means that it gained 2 electrons. So we're going to add those 2. So 3 times 6 is 18, plus 2 is 20, plus 4 is 24 electrons. All right, so we're going to do carbon in the center, and we're going to draw those 3 oxygens around it and connect them. There's sort of skeletal structure there. So that's 6 electrons that we've distributed through those bonds, and now we're going to do the rest around those oxygens first. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. All right, so we've got all of the electrons distributed. We've got all 24 accounted for. We can't add any more. All of the oxygens have an octet, but that carbon does not. It has 6 electrons through those bonds. It needs 1 more. So we can pick one of those oxygens, and we can push and make a double bond. So we end up with this guy here, CO. And I don't want to forget my lone pairs. All right, so we end up with this structure here. And we're going to do our brackets and our charge, okay? But we could just as easily have ended up with this structure. Put the double bond over here on this oxygen. All right, or we could have put it on the bottom one. All right, so all of these would be correct answers for the Lewis structure, but they also are actually all existing in reality. So these different forms, all right, of the same molecule are called resonance structures. All right, so some molecules can be described by more than one Lewis structure. You could put the double bond on oxygen 1, 2, or 3. So the atoms are all in the same location, but the electrons are in different locations. We just moved that double bond around. So all of these structures, we call these resonance structures, and we sometimes draw those with this double arrow, sort of showing that they can actually, this carbonate ion can kind of flip between these 3 different forms. Technically, that double bond can move around in this polyatomic ion. And so we can draw what's called a resonance hybrid to show that movement of electrons. So the resonance hybrid of this molecule would look like this. So we've got the carbon and the 3 oxygens. And then to show that double bond that can move around, we would draw a dotted line. These are supposed to be dotted lines. All right, so that dotted line shows that either one of these 3 bonds could be double bonds, and that pair of electrons actually does sort of travel and rotate around. So my dotted lines are not very good, but they're supposed to be dotted lines. I won't have you drawing resonance hybrids, but I will ask you to draw resonance structures of different molecules, so the different bonding patterns that you might see. And by the way, sorry, before I move on, these dotted lines represent the fact that those electrons are delocalized. In other words, they're not static, they're not staying in this one bond, this one double bond, that double bond can actually move around, that those electrons can actually travel, right? Electrons, when we draw Lewis structures, we kind of visualize them as being static. But remember, electrons are always moving around. Always, always. So we can determine if you have a molecule with multiple resonance structures that are maybe not equivalent. We can determine what the best resonance structure, most likely resonance structure is by determining the formal charge. The formal charge is the charge on an atom if all electrons are actually shared equally. And it's calculated using this formula. The formal charge equals the number of valence electrons minus the number of owned, quote unquote, electrons. And what I mean by owned electrons are any and all lone pair electrons and half of the bonding electrons. So let's look at an example. O3, ozone. All right, here's the structure for ozone. And get my lone pairs in here. 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4. Okay, so the number of valence electrons that oxygen has is 6. So for each of those oxygens would have 6 valence electrons. All right, and then now for the owned electrons, all right, this oxygen, the first one on the left, has 2 lone pairs, so that's 4 electrons that it owns from lone pairs. And remember, each of these bonds represents 2 electrons. So we would say that half of those belong to the oxygen on the left. So that's 1, 2, 3, 4, 5, 6. The oxygen in the middle has 2 lone pairs and 1, 2, 3 from bonds. So it has 5 quote-unquote owned electrons. And then the one on the left has 6 from lone pairs and 1 from the bond, so it has a total of 7 owned electrons. So now we're just going to do some subtraction. All right, 6 minus 6 is 0, 6 minus 5 is 1, 6 minus 7 is -1. All right, so we would say that the formal charges on the oxygens here, we could write that as this one has a formal charge of 0, this one has a formal charge of 1, and this one has a formal charge of -1. And we might write a positive to indicate that that's a +1. Okay, so those are the formal charges. Now, when we are calculating formal charges, some rules are that the sum of all the formal charges needs to add up to the total charge on the molecule. In this case, they add up to 0, which is good because this molecule is not charged. It has a 0 charge. So that's just a way to check yourself, I suppose, to make sure you didn't make any grand errors. If it's an ion, they'll add up to the charge of the ion. So formal charge is useful because it can be used to determine the best resonance structure and in molecules that have multiple potential resonance structures. So let's look at an example of one of those. NCO-. This is a polyatomic ion. So nitrogen has a charge of, has 5 valence electrons, and carbon has 4 valence electrons, and oxygen has 6 valence electrons, and it has a -1 charge, so we've got to add another electron there. So 5 plus 4 is 9, plus 1 plus 16 electrons. Okay? So we want the least electronegative atom to be in the center. So we're going to start with carbon here. We'll just draw it like this, NCO. So we could have this valence. We end up, if we draw out all the different possible structures we could have this arrangement here, or we could have this arrangement here, triple bond, and technically I should get my brackets out. And then the third arrangement we could have is this one, triple bond to the oxygen. All right, all of these 3 structures are correct in the sense that they have 16 electrons and each atom fulfills the octet rule. So which one is correct? Which one is the best, most likely structure that this atom actually has? Well, we can figure that out using formal charges. So valence electrons minus owned electrons. So nitrogen has 5 valence electrons, carbon has 4, and oxygen has 6. In this first structure, the nitrogen has 1, 2, 3, 4 owned electrons. The carbon has 1, 2, 3, 4. And the oxygen has 1, 2, 3, 4, 5, 6. So 5 minus 4 is 1, 4 minus 4 is 0, 6 minus 6 is 0. Let's do it for the second one. Nitrogen carbon and oxygen always have the same number of valence electrons. In this atom, or in this molecule as drawn, the nitrogen has 1, 2, 3, 4, 5 owned electrons. The carbon has 1, 2, 3, 4. And the oxygen has 1, 2, 3, 4, 5, 6, 7. So 6 from the lone pairs and 1 from the bond. So the formal charges here would be 0, 0, and -1. And then lastly, this one here, we'll set up the valence electrons. This nitrogen has 6, 7 owned electrons. The carbon has 1, 2, 3, 4. And the oxygen has 2, 3, 4, 5. So those charges here would be -2, 0, and +1. Okay, so we have 3 different options here. The rule with formal charges is that the smaller formal charges are best. Okay, so we've got 1, 0, 0, 0, 0, -1, and -2, 0, 1. So that last one, we can pretty much rule that one out. That's not going to be our best structure. It has larger formal charges, all right? But the other two are pretty equivalent, so how are we going to choose between them? Well, the next rule says that the more electronegative atom should have the negative formal charge. So in this one, nitrogen is fairly electronegative, and it has a positive charge. But in the second structure, the oxygen, which is the most electronegative atom in this molecule, has a negative charge, a -1 charge. So this would be the winner, the winning structure. This is the one that's most likely to be the one that exists. Now these technically they're all resonance structures, and the electrons do probably move between them, and all of them exist. But the one that spends the most time in existence is this one here, because this will be the most stable form of this molecule. All right. I'm also going to use this example to show you that formal charges also explain why we always put the least electronegative atom in the center. Because if we take this molecule and we rearrange it and we don't have carbon in the center, we could do something like this, where we do carbon and nitrogen's in the center. All right, we still have our 16 electrons. And we could do this one here. All right, these are also possible resonance structures. But if we calculate the formal charges, so we do the valence electrons for each, and we subtract by the owned electrons. So this carbon has 2, 3, 4, 5 owned electrons. The nitrogen has 1, 2, 3, 4, and the oxygen has 6 plus 1, 7. So this is going to have -1, +1, -1. All right, it's a lot of formal charges. That's 3 different formal charges there. Not ideal. And then this carbon on the second one has 5 owned electrons. The oxygen has 4, and the nitrogen has 7, -1, 2, -2. Okay, so neither of these structures is very stable compared to these two in particular up here. So those are the two that will dominate for this molecule, the double bond and the triple bond form. All right, so I told you that there are rules for bonding, and there's always exceptions to the rule. So I am going to tell you some of the exceptions to the octet rule where Lewis structures actually violate the octet rule. But again, I'm not going to hold you accountable for these, but just know they do exist. There are some molecules that have incomplete octets. So BF3 is one. So BF3's Lewis structure looks like this. Boron in the center and fluorines around the outside. All right. And each of the fluorines has a full octet, but the boron in the center just has 6 electrons around it, and it's okay. It's cool like that. Some other exceptions, free radicals. These are odd electron species. So if you haven't noticed, every one that all the examples we've done have an even number of electrons. Well, nitrogen dioxide, nitrogen has 5, and oxygen has 6. So 2 times 6 is 12, plus 5, 17 electrons. It's an odd number. So it ends up looking something like this. One, two, three, 4. And then there's just 1 electron sticking there. So it also doesn't fulfill the octet rule because that oxygen only has 7 electrons around it, not 8 like it should. These guys are really reactive and unstable because they really are not comfortable without having an octet. That oxygen really wants another electron. It'll actually go around and steal an electron from other things and start this sort of chain reaction of electron stealing. And that's what free radicals do. Another exception is that there are some molecules or some atoms that can have expanded octets. So basically any elements that are in period 3 or lower are large enough to have more than 8 valence electrons, and that's because you start getting into the d orbitals and when you get into the 4th row of the periodic table. So sulfur, for example, is one of these. So sulfur, SF6, I guess 1, 2, 3, 4, 5, 6, all right, has 6 fluorines around it. And each of those fluorines has a full octet. We could do all the lone pairs for them. All right, but notice that the sulfur has 6 bonds. That's 12 electrons that it can hold. All right, so it can have what we call an expanded octet. So all of these Lewis structures that we're drawing, they are 2-dimensional. They're flat on paper. But molecules aren't 2-dimensional. They're 3-dimensional. They exist in 3D. All right. So if we draw the Lewis structure of methane, for example, it looks like this, CH4. All right. We would draw it flat on this paper. And when we draw it this way, it makes it look like the angle between these bonds here is 90 degrees, right? But if we were to try to draw it in 3 dimensions, and the way that chemists do this, like on paper, is they draw using straight lines and wedges and dashes. So we call it the dash and wedge structure. So the dashed one is like the hydrogen. Imagine that hydrogen going into the page, like it's going out the back side. And then the solid wedge represents an atom coming out of the page at you. So it's an attempt to try to draw the molecule in 3 dimensions on a flat piece of paper, okay? So the bond angle now, if it's 3-dimensional, is much greater. We would say it's 109.5 degree angle, all right? So those atoms actually they're spread out a little bit more in space in 3 dimensions. And so the model that helps us to view molecules in 3 dimensions is the Vesper model, VSEPR. It stands for Valence Shell Electron Pair Repulsion. Drink of water. So it's based on this idea that, You know, atoms have electron clouds around them, and their electron clouds, which are all negatively charged, are going to repel each other because like charges attract. I like to think of it as social distancing for atoms in a molecule. So basically, when you have a carbon, if you have this carbon and it has 4 hydrogens bonded to it, those hydrogens, basically, they want their personal space. They want to be as far apart from each other as physically possible and have as much space to themselves as they can. And so we can use this theory in order to determine the shape of different molecules. There's sort of a formulaic way of doing this. The Vesper formula is going to be in this AXE format. So A just represents the central atom. We're always going to be talking about it, the central atom. We're going to look at the central atom and we're going to say, how many bonding domains does it have? And we're going to represent that with X. Now, the bonding domains is just like the bonding directions. It's not the number of bonds. So a single bond, a double bond, and a triple bond all count as one bonding domain. Okay? One bonding domain. So it's not about the number of bonds, it's about the number of bond directions. And then we also count the number of non-bonding domains, also known as the lone pairs. So let's work an example one. For water, if we look at water, H2O, right, we draw out the Lewis structure for water. Would look like this. All right, so if we were going to write out the Vesper formula for this, we're looking at the central atom, which is the oxygen. All right, and it has 2 bonds, 2 bonding domains coming out the right and left sides, and it has 2 lone pairs. So we do AX subscript 2, E subscript 2 would be the formula, the Vesper formula for this. All right, so when we are drawing molecules in 3 dimensions and naming we can talk about the geometry of their shapes. There's sort of 2 geometries we can refer to. So there's the electron domain geometry, and there's the molecular geometry. All right, so the electron domain geometry looks at the arrangement of all the electron domains. So that includes the bonds and the lone pairs. All right, the molecular geometry is only looking at the bonds, the bonding domains. In other words, where the atoms are. So, for example, if we look at water again, water's Lewis structure looks like this. All right, that's the 2-dimensional Lewis structure. All right, in this 2-dimensional Lewis structure, it looks like water is linear. It's a straight molecule. But if we look at its 3D structure, all right, and we draw it out like this, we see that oxygen has 2 lone pairs, and I'm going to draw them in these little cloud bubbles. All right, and then it's got 1 hydrogen coming out of the page and 1 hydrogen going into the page. All right, so it's actually, if we take out those lone pairs, so this is the electron geometry. Electron, of the electron domain geometry. All right, and it has 4 electron domains. So we call this a tetrahedral shape. All right, but if we just kind of ignore those or not show the electron domains and we're just looking at the placement of the atoms, of the bonds, all right, then this is the molecular geometry. And in this case, there's only 2 bond domains. So we call this shape bent. All right, so water is not linear. It's not a straight molecule. It's a bent molecule. And it's bent because it actually has 4 things around it sticking out in different directions. 2 lone pairs and 2 hydrogens. Alrighty, so the next couple of pages are basically a worksheet that we're going to fill out to learn the different shapes and names and different geometries of molecules. So we can have molecules that have 4 domains. All of these in this first chart here, they all have the same electron geometry, and that shape is called tetrahedral. They all have a tetrahedral electron geometry. If we were to write the Vesper formula for this one, it would be AX4. There's no lone pairs. This is the central atom, and there's 4 bonding domains coming off of it. This one has 3 bonding domains and 1 lone pair, so it'd be AX3E. And this one has 2 bonding domains and 2 lone pairs. So this one has 4 bonds, no lone pairs, 3 bonds, 1 lone pair, 2 bonds, 2 lone pairs. All of them still add up to 4 electron domains. So an example that we've already done with this one would be methane, CH4. All right, and we call this shape tetrahedral. And the bond angle between those hydrogens is 109.5 degrees. For the second one here, a good example would be Ammonia Nh3. The nitrogen has a lone pair and 3 bonding domains. And this shape is called, oopsie daisy. This shape is called Trigonal Pyramidal. And these hydrogens are a little bit less than 109.5 degrees apart. And that's because this lone pair here actually takes up a little bit of extra space and kind of pushes on those hydrogens a little and pushes them a little bit closer together. So this bond angle here is less than 109.5. And then this third box, we're going to put water. Oxygen and 2 hydrogens and our lone pairs right here. Okay, we call this shape bent, and this is going to be even a little bit less than 109.5 degrees. Okay, again, because these lone pairs actually push, they kind of take up a little bit more space and repel those atoms and those bond arms a little bit more. These are some shapes that have 3 domains, 3 total domains, electron domains. We call these Trigonal Planar is the electron geometry here. So this one has 3 bonds and no lone pairs. So this would be the formula. And this one has 2 bonds and 1 lone pair. So it would have this formula here. All right, an example of the first one would be, I think we drew this one out before, I can't remember. So this carbon has 3 bonding domains. It has 4 bonds, but only in 3 different directions. So it still has 3 bonding domains. Erase that. This shape is called Trigonal Planar. And the bond angle that we see here is 120 degrees. So this is actually a molecule that is in 2 dimensions. It's all on 1 plane. And then a good example of this one would be O3, ozone, which we saw before. All right, so ozone looks like this. The oxygen in the middle has a lone pair on it. Sorry, this is sloppy. I'm going to redraw that. So there is a lone pair on this oxygen. All right, so ozone looks like this. So the central oxygen has two bond domains coming out of it, even though it's 3 bonding arms. Remember, a double bond, triple bond, it still just counts as 1 bonding domain. And this is a linear shape. Nope, sorry, just kidding. It's bent. Just like the water molecule, it's bent, okay? And this bond angle here is slightly less than 120 degrees. Because again, that lone pair takes up a little bit more space and repels these bonds a little bit more. So, and then the last one on this page, this electron geometry shown here is called a linear molecule. It's just got 2 bonds and no lone pairs, so a formula of AX subscript 2. An example would be carbon dioxide, which looks like this. All right, so the carbon in the center just has 2 bond domains coming out of it, and this is still a linear shape, and that bond angle here is 180 degrees. All right, so those are the ones that I would have you draw Lewis structures of. Well, I won't have you draw Lewis structures of molecules that are exceptions to the octet rule. I could give you examples of those molecules. I could give you the Lewis structures and then ask you what is the geometry, the electron geometry or the molecular geometry. So you should fill out this table and keep it handy because you can use it on the homework, you can use it on the test. I won't make you memorize these different shapes and names, but you do need to know how to read this table and use it. So this shapes that have 5 electron domains are called trigonal, bipyramidal, so the simplest one is one that has 5 bond domains and 0 lone pairs. Its formula would be this. An example is PF5, 1, 2, 3, 4, 5. Each of these fluorines has 3 lone pairs that I'm too lazy to draw right now. All right, but notice that the phosphorus in the center has 5 bonds coming out of it. And of course, this is going to be called the same thing as the electron geometry, trigonal bipyramidal. Trigonal bipyramidal. And the bond angles, there's 2 of them, okay? So the bond angle between these guys and these on this sort of middle plane here is 120 degrees. All right, but the bond angle between this top one and those middle ones, bless you, sweetie, is 90 degrees. Now, the next one down, we've got 4 bond arms and 1 lone pair, AX4E, and this one could be demonstrated by SF4, which looks like this. Each of these fluorines would have 3 lone pairs, and this sulfur has 4 bonds and 1 lone pair. This shape is called seesaw. Because if you look at it, it looks kind of like a seesaw. Like this is the base of the seesaw. And then like if you had somebody sitting right here and somebody sitting right here, do you see that? And I could go up and down, up and down. Well, hopefully you do. So the bond angles here again are, so this bond angle right here on this plane is going to be a little bit less than 120. And the bond angle between this, the top and bottom ones to those middle ones is going to be about 90 degrees. This one has 3 bonds, 2 lone pairs, An example of it would be chlorine trifluoride. And this is called T-shaped. And the bond angles here are all 90 degrees. And then this last one has 2 bond arms and 3 lone pairs. And an example of this one would be I3. And I can't actually recall the structure for this one. Iodine has 7 times 3 is 21. Valence electron 2, 4, 6, 8, 10. 12, 14, 16, 18, 20, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And I'm messing it up. Well, I'm not going to get the structure right for now because I can't remember the rules for the exceptions. So, whatevs. Just know it has 2 bonding arms, and I guess this middle one has 3 lone pairs somehow. So, it's probably an ion. Anyway, this has a linear structure. It has a linear structure because the 2 bonding atoms are 180 degrees apart. Shapes that have 6 domains, we call them octahedral. I don't really know why, because octa means 6, but that's the name of the shape, octahedral. And this simple one that has all bonding pairs, so there's 6 bonding pairs, 0 lone pairs. This one has 5 bonding pairs, 1 lone pair, 4, and 2. Formulas look something like this. Sorry, they're a little sloppy. And some examples. SF6. And this shape is, this electron geometry and molecular geometry are called octahedral. And these bond angles are all 90 degrees apart. An example of this one is BR. F5. And this shape is called square. Pyramidal. And these bond angles are all still 90 degrees apart. And then this last one, an example is xenon trifluoride. I think my stylus might be running out of batteries. And it's called square planar. And still, the bond angles are 90 degrees between all of these. All right, so you could be asked to draw a Lewis structure, and then you might be asked, what's the electron geometry and what's the molecular geometry of this Lewis structure? And so you'll be comparing it to this table, essentially. Or you might be given a Lewis structure and asked, what's the electron geometry? What's the molecular geometry? So the electron geometry has to do with the total domains. All three of these have the same electron geometry, but they each have a different molecular geometry. All right. Okay. So remember we talked about electronegativity before, and I said, molecules can be polar, or bonds can be polar or nonpolar, depending on whether electrons are shared equally or unequally. Not just a bond can be polar, but the whole molecule can be polar as well. So molecules that have regions of partial positive and partial negative charges are polar molecules. So in order for a molecule to be polar, it needs to have at least one polar bond. That's kind of a duh. But it also needs to have a total net dipole moment. So for example, all right, water, all right, water is a polar molecule because it has polar bonds. Oxygen is an electron hog. It has an electronegativity of like 3.5, and hydrogen has an electronegativity of like 2.1. So there is definitely, these two bonds are polar, and the dipole moment, because this molecule is bent, all right, the dipole moment points up towards that oxygen. All right, so we say that this molecule is polar. It has polar bonds, and it has a net dipole moment, as opposed to this molecule here, carbon dioxide. All right, oxygen has a much higher electronegativity than carbon, so these two bonds are polar, but they are pulling, the dipole moments are in opposite directions, and they cancel each other out. So in other words, there's no partially positive and partially negative ends. These ends are both partially negative. So this one is nonpolar, right? Because those dipole moments cancel each other out. In other words, a sort of tip for you here is that if all the atoms off the central atom have the same electronegativity and there are no lone pairs, then the molecule is nonpolar. And that's exactly what we see with carbon dioxide. There are two oxygens. They have identical electronegativities, and there are no lone pairs on that carbon, and so that means that this is a nonpolar molecule. Let's try a couple more. Try these. Do them in black. So we've got this molecule here, and this one here. These are F's for fluorine. And then lastly, this one here. All right, so this first one, carbon and oxygen. So carbon and hydrogen, that's not a polar bond. But carbon and oxygen do have a polar bond. So the dipole moment's going to be pointing up like this. This molecule is polar. The second one, carbon and fluorine bonds are polar. All right, but all of these are pulling in opposite directions. All right, and sort of canceling each other out. In other words, all of these have the same electronegativity, and there's no lone pairs on the central atom. So this is nonpolar. And in the last one, there's only one polar bond, that carbon-fluorine bond, pulling in that one direction. So this molecule will be polar. All right, we're almost done with this marathon. And that is where we are dipping into Chapter 5 just a little bit, just to touch on valence bond theory, that third theory that explains bonding. So valence bond theory says that covalent bonds form when atomic orbitals of two atoms overlap and form hybrid orbitals. So it's a little bit more than Vesper and the Lewis structure. So what does this mean? All right, so if we take the number of electron domains, we can sort of simplify this. And we take the number of electron domains, all right? That will tell us the number of orbitals that are mixed according to valence bond theory. So if we have the number of electron domains here, all right, and we say that these orbitals hybridize. Orbitals that hybridize. Hybridize. All right, and this is the name of the hybrid orbital. And this is the shape. All right, so for a molecule that has two electron domains, we say that two orbitals overlap. So there's the s orbital and then the first p orbital. All right, we see that they overlap or they hybridize and they form this sp orbital. All right, so we call that hybrid orbital the sp, and that molecule has a linear shape, which we would say that for any molecule that has an electron domain, two electron domains. Molecules that have three electron domains have a trigonal planar shape, so that name is not new. But valence bond theory says that they have a hybridized orbital of an s and two p's. So they have three hybridized orbitals. So we say that it's sp2, that one s and two p orbitals have fused together to form these hybrid orbitals. All right, same thing, the pattern keeps going. So for a molecule that has four electron domains, we say that the s and the three p's hybridized, and so we get an sp3 hybrid orbital, and so on and so forth. So it's these fused hybrid orbitals where the shared electrons hang out. And the shape names are all really the same that we saw already from the electron domains. But so the names stay consistent in valence bond theory. So in valence bond theory, it says that these hybrid orbitals are overlapping, and that's where the electrons are being shared. And then if a molecule has a double bond or a triple bond, that's sharing of electrons in those extra p orbitals, those incomplete p orbitals. So we can determine the so we can determine the hybrid orbitals in different molecules by counting the lone pairs and the atoms around the center. In other words, we're counting the electron domains around the center. And I sort of count it like, so if there's one, then that's S, or I count it like this, S, P, 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 D. There's 3 P domains, and then there's 5 Ds, but we only would go up to 2. Okay, so let me show some examples. So for water here, the central molecule, oxygen, has 2 bond arms and 2 lone pairs. Okay, so it has 4 electron domains. All right, there's 4 electron domains, so that would be sp3. SPPP. That's 4 domains. All right. For the xenon here, the central one, all right, it has 2 bonding 2 lone pairs and 4 bonding domains for a total of 6. So that's S, P, 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 and D, D. So that would be sp3, D2. That's a total of 6 orbitals hybridized. S, P, 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 D, D, total of 6. And then this guy right here, this carbon, has 3 bonding domains, no lone pairs. So a total of 3 electron domains means sp2, that it's sp2 hybridized. All right, so there will be questions in the homework that ask you, what's the hybridization of this atom in this molecule? Basically, all you're doing is counting the number of electron domains, and then you are picking the right orbitals to be hybridized here. So sp3 is spp. That's 4 different orbitals that have combined because 4 electron domains. I hope I'm explaining that clearly. All right, so the last thing to talk about is sigma and pi bonds, and I'm only going to be doing this very superficially. So sigma bonds are basically what we call single bonds, and pi bonds are what are involved in double and triple bonds. So sigma bonds, and this is the Greek letter sigma, the orbitals overlap end to end. So if you have 2 carbons, all right, we say that these orbitals here are reaching out and overlapping. Those are sigma orbitals, and you have electrons that are shared in here. Pi bonds overlap. Pi bonds reach up. So sigma bonds are sort of horizontal, and pi bonds are above and below. All right, these are just sort of kind of like orbitals, orbital shapes. They're 3-dimensional zones where electrons can fly around and be shared. So the pi bonds are formed by those unhybridized p orbitals, those leftover p orbitals, and we see them in double and triple bonds. So if you have a double bond, all right, so if you have, let's say, a carbon-carbon double bond, all right, one of those bonds is a sigma bond, and the other one is a pi bond. If you have a triple bond, all right, one of those is a sigma bond, and the other 2 are both pi bonds. Okay, so all single bonds and one of the bonds in double and triple bonds are sigma, and any additional bonds beyond a single bond are made up of pi bonds. So the only type of question I'd ask you about this is I'd ask you to sort of count the number of sigma and pi bonds in these molecules. So if I make sigma red, then single bonds are both sigma, and one of these is a sigma bond. So this has 3 sigma bonds and 1 pi bond. 3 sigma, 1 pi. This one here has 1, and one of these is a sigma, so that's 2 sigma bonds. And then the other 2 bonds in that triple bond are pi bonds. So I could give you a molecule, a relatively much larger molecule, and just ask you how many sigma and pi bonds are there in here, and you should count all of the single bonds as sigma, and one each of the double and triple bonds as sigma. So this is maybe a confusing picture, but is trying to show you sort of how this valence bond theory works and how these orbitals have these different shapes. So this is a molecule of ethene, which looks like this. It's trying to show you the different hybridized orbitals and how the sigma bonds and pi bonds work. So I won't test you on this. It's very confusing. Oops, my stylus fell apart. There, maybe now it will work better now that I've fixed that. Alrighty, so these are the hybridized sp2 orbitals. In green here, those bubbles. And you can see these electrons here being shared. That's a sigma bond right here, showing you the sigma bond. So like this bond right here between the two carbons. All right, but then this second bond here, this is the pi bond right here. All right, and that's illustrated by these orange lobes up here. So the pi bond runs sort of up or north and south, I guess you can say. So it's a very complicated sort of geometry, kind of getting into quantum mechanics here. So we're not going to get into it that much, but just to give you a visual of what we're talking about with these sigma and pi bonds in these pictures here. Okay, but all I'm going to ask you to do in terms of questions potentially on tests or homework is to simply count the number of sigma and pi bonds. You won't have to draw them like this. That's very complex. And now